Theoretical work on the question stagnated for decades, and so did measurement of the level of CO2 in the atmosphere. 10 *. Radiation math. A few scientists dissented from the view that changes of CO2 could have no effect. An American physicist, E.O. Hulbert, pointed out in 1931 that investigators had been mainly interested in pinning down the intricate structure of the absorption bands, which offered fascinating insights into the new theory of quantum mechanics, and not in getting accurate absorption coefficients. Hulbert's own calculations supported Arrhenius's estimate that doubling or halving CO2 would bring something like a 4 degrees Celsius rise or fall of surface temperature, and thus the carbon dioxide theory of the ice ages is a possible theory. 11. Hardly anyone noticed this paper. Hulbert was an obscure worker at the U.S. Naval Research Laboratory, and he published in a journal, the Physical Review, that few meteorologists read. Their general consensus was the one stated in such authoritative works as the American Meteorological Society's 1951 Compendium of Meteorology. The idea that adding CO2 would change the climate was never widely accepted and was abandoned when it was found that all the long-wave radiation that would be absorbed by CO2 is already absorbed by water vapor. 11a. Radiation math. Even if people had recognized this was untrue, there were other well-known reasons to deny any greenhouse effect in the foreseeable future. These reasons reflected a nearly universal conviction that the Earth automatically regulated itself in a balance of nature. Getting to specifics, scientists repeated the plausible argument that the oceans would absorb any excess gases that came into the atmosphere. 50 times more carbon is dissolved in seawater than in the wispy atmosphere. Thus the oceans would determine the equilibrium concentration of CO2, and it would not easily stray from the present numbers. Public opinion. The oceans. If somehow the oceans failed to stabilize the system, organic matter was another good candidate for providing what one scientist called homeostatic regulation. 12. The amount of carbon in the atmosphere is only a small fraction of what is bound up not only in the oceans but also in trees, peat bogs, and so forth. Just as seawater would absorb more gas if the concentration increased, so would plants grow more lushly in air that was fertilized with extra carbon dioxide. Rough calculations seem to confirm the comfortable belief that biological systems would stabilize the atmosphere by absorbing any surplus. One way or another, then, whatever gases humanity added to the atmosphere would be absorbed if not at once, then within a century or so, and the equilibrium would automatically restore itself. As one respected expert put it baldly in 1948, the self-regulating mechanisms of the carbon cycle can cope with the present influx of carbon of fossil origin. 13. Simple models. Yet the theory that atmospheric CO2 variations could change the climate was never altogether forgotten. An idea so simple on the face of it, an idea advanced, however briefly, by outstanding figures like Arrhenius and Chamberlain, had to be mentioned in textbooks and review articles if only to refute it. Arrhenius's outmoded hypothesis persisted in a ghostly afterlife. Calendar's advocacy, the greenhouse warming theory, found a lone advocate. In 1938 an English engineer, Guy Stewart Callender, tried to revive the old idea. An expert on steam technology, Callender apparently took up meteorology as a hobby to fill his spare time. 14. Many people, looking at weather stories from the past, had been saying that a warming trend was underway. When Callender compiled measurements of temperatures from the 19th century on, he found they were right. He went on to dig up and evaluate old measurements of atmospheric CO2 concentrations. He concluded that over the past 100 years the concentration of the gas had increased by about 10%. This rise, Callender asserted, could explain the observed warming. For he understood, perhaps from Hulbert's calculation, that even if the CO2 in the atmosphere did already absorb all the heat radiation passing through, adding more of the gas would raise the height in the atmosphere where the crucial absorption took place. That, he calculated, would make for warming. As for the future, Callender estimated, on flimsy grounds, that a doubling of CO2 could gradually bring a 2 degrees Celsius rise in future centuries. Aware that industrial emissions were already far greater than in Arrhenius's day, Callendar saw this warming as a matter of present interest. He hinted that over the centuries it might even trigger a shift to a self-sustaining warmer climate, which did not strike him as a bad prospect. 15. But future warming was a side issue for Callendar. Like all his predecessors, he was mainly interested in solving the mystery of the ice ages. Callendar's publications attracted some attention, and climatology textbooks of the 1940s and 1950s routinely included a brief reference to his studies. But most meteorologists gave Callendar's idea scant credence. In the first place, they doubted that CO2 had increased at all in the atmosphere. The old data he had sorted though were untrustworthy, for measurements could vary with every change of wind that brought emissions from some factory or forest. Already in the 19th century scientists had observed that the level of the gas rose, for example, near a flock of sheep busy exhaling the gas, and dropped in London during the inactivity of a bank holiday. 16. As late as 1956 nobody seems to have noticed that a published graph of CO2 measurements since 1800 showed an obvious upward trend. If in fact the level was rising, scientists felt that could only be detected by a meticulous program stretching decades into the future. 17 asterisk. G.S. Callendar, little-known pioneer. The objections that had been raised against Arrhenius also had to be faced. Wouldn't the immense volume of the oceans absorb all the extra CO2? Callendar countered that the thin layer of ocean surface waters would quickly saturate, and it would take thousands of years for the rest of the oceans to turn over and be fully exposed to the air. 18. But nobody knew the actual turnover rate, and it seemed that the oceans would have time to handle any extra gases. According to a well-known estimate published in 1924, even without ocean absorption it would take 500 years for fuel combustion to double the amount of CO2 in the atmosphere. 19. There was also the old objection, which most scientists continued to find decisive, that the overlapping absorption bands of CO2 and water vapor already blocked all the radiation that those molecules were capable of blocking. Callendar tried to explain that the laboratory spectral measurements were woefully incomplete. 20. Gathering scattered observational data, he argued that there were parts of the spectrum where the CO2 bands did not overlap with water vapor absorption. Some scientists found this convincing, or at least kept an open mind on the question. But it remained the standard view that, as an official U.S. Weather Bureau publication put it, the masking of CO2 absorption by water vapor was a fatal blow to the CO2 theory. Therefore, said this authority, no probable increase in atmospheric CO2 could materially affect the balance of radiation. 21. Most damaging of all, Callendar's calculations of the greenhouse effect temperature rise, like Arrhenius's, ignored much of the real world's physics. For example, as one critic pointed out immediately, he only calculated how heat would be shuttled through the atmosphere by radiation, ignoring the crucial energy transport by convection as heated air rose from the surface. This deficiency would haunt greenhouse calculations through the next quarter century. Worse, any rise in temperature would allow the air to hold more moisture, which would probably mean more clouds that would reflect sunlight and thus preserve the natural balance. Callendar admitted that the actual climate change would depend on interactions involving changes of cloud cover and other processes that no scientist of the time could reliably calculate. Few thought it worthwhile to speculate about such dubious questions, where data were rudimentary and theory was no more than hand-waving. Better to rest with the widespread conviction that the atmosphere was a stable, automatically self-regulated system. The notion that humanity could permanently change global climate was implausible on the face of it, hardly worth a scientist's attention. 22. The scientists who brushed aside Callendar's claims were reasoning well enough. Subsequent work has shown that the temperature rise up to 1940 was, as his critics thought, mainly caused by some kind of natural cyclical effect, not by the still relatively low CO2 emissions. And the physics of radiation and climate was indeed too poorly known at that time to show whether adding more gas could make much difference. Yet if Callender was mistaken when he insisted he could prove global warming had arrived, it was a fortunate mistake. Research by definition is done at the frontier of ignorance. Like nearly everyone described in these essays, Callender had to use intuition as well as logic to draw any conclusions at all from the murky data and theories at his disposal. Like nearly everyone, he argued for conclusions that mingled the true with the false, leaving it to later workers to peel away the bad parts. While he could not prove that greenhouse effect warming was underway, he had given sound reasons to reconsider the question. We owe much to Callender's courage. His claims rescued the idea of global warming from obscurity and thrust it into the marketplace of scientific ideas. Not everyone dismissed his claims. Their very uncertainty attracted scientific curiosity. The theory restored, 1950 to 1958. The complacent view that CO2 from human activity could never become a problem was overturned during the 1950s by a series of costly observations. This was a consequence of the Second World War and the Cold War, which brought a new urgency to many fields of research. American scientists enjoyed massively increased government funding, notably from military agencies. The officials were not aiming to answer academic questions about future climates, but to provide for pressing military needs. Almost anything that happened in the atmosphere and oceans could be important for national security. Among the first products of these research efforts were new data for the absorption of infrared radiation, a topic of more interest to weapons engineers than meteorologists. 23. Government. The early experiments that sent radiation through gases in a tube, measuring bands of the spectrum at sea level pressure and temperature, had been misleading. The bands seen at sea level were actually made up of overlapping spectral lines, which in the primitive early instruments had been smeared out into broad bands. Improved physics theory and precise laboratory measurements in the 1940s and after encouraged a new way of looking at the absorption. Scientists were especially struck to find that at low pressure and temperature, each band resolved into a cluster of sharply defined lines, like a picket fence, with gaps between the lines where radiation would get through. 24, as Hulbert and Callender had claimed, the most important CO2 absorption lines did not lie exactly on top of water vapor lines. Instead of two overlapping bands, there were two sets of narrow lines with spaces for radiation to slip through. So even if water vapor in the lower layers of the atmosphere did entirely block any radiation that could have been absorbed by CO2, that would not keep the gas from making a difference in the rarefied and frigid upper layers. Those layers held very little water vapor anyway. And scientists were coming to see that you couldn't just calculate absorption for radiation passing through the atmosphere as a whole, you had to understand what happened in each layer, which was far harder to calculate. External input. Digital computers were now at hand for such calculations. The theoretical physicist Louis D. Kaplan decided it was worth taking some time away from what seemed like more important matters to grind through extensive numerical computations. In 1952, he showed that in the upper atmosphere, adding more CO2 must change the balance of radiation. 25. Radiation math. But would adding carbon dioxide in the upper layers of the air significantly change the surface temperature? Only detailed computations, point by point across the infrared spectrum and layer by layer down through the atmosphere, could answer that question. By 1956, such computations could be carried out thanks to the increasing power of digital computers. The physicist Gilbert N. Plass took up the challenge of calculating the transmission of radiation through the atmosphere. He too did it out of sheer curiosity, as a diversion from his regular work making calculations for weapon engineers. He nailed down the likelihood that adding more CO2 would increase the interference with infrared radiation. Going beyond this qualitative result, Plass calculated that doubling the level would bring a 3 to 4 degrees Celsius rise. Assuming that emissions would continue at the current, 1950s, rate, he expected that human activity would raise the average global temperature at the rate of 1.1 degrees C per century. 26.